Right. Okay, so last time we were here, we were discussing how to deal with this situation where we have a gas which is collected over water and how we can find the pressure of that gas based on two things, based on the barometric pressure, which is the atmospheric pressure, and also based on the vapor pressure of water, right? And just to remind you again that this method only works with, I'm talking about the method of collecting gas in this way. Only works with gases that are not soluble in water, right? So you would not use this to collect something like ammonia or hydrogen chloride. You would use this for example, oxygen, nitrogen, or some of the hydrocarbon gases like methane, propane, and so on, all right? So just to remind you that basically this is the equation that you use to calculate the pressure of the gas that is collected here, right? Because remember, what is collected here would be gas that is wet. In other words, it has some water vapor with it. So you have to take into account that there are the vapor pressure of the water that you have to take into account in calculating the pressure of the gas. You basically subtract that value from the barometric pressure, and that will give you the pressure of the gas. The barometric pressure, of course, you can measure using the barometer, and the vapor pressure of the water, you'd have to obtain their tables that are available, which gives you the different temperatures or the different vapor pressures of water at different temperatures, right? So those are the two pieces of information that you need in order to calculate the pressure of the gas. Okay, so with that said, let's look at this example. I'm gonna need some space here, so let me see here. Maybe if I bring this up. Okay, I think this should be sufficient. All right, so this question says, okay, so this question says you have hydrogen that is produced, and it gives you the equation that explains the production of hydrogen based on this reaction right here. It says that it's collected at 22 degrees Celsius when the barometric pressure is 742 torr. Now, there's a missing piece of information here which is necessary, and that is the vapor pressure of water at 22 degrees Celsius. So what I'm going to do is do a little Google search to see what the vapor pressure vapor pressure of water at 22 degrees. And let's see what this says. So at 22 degrees, it's 19.8 millimeters mercury, right? So that's an additional piece of information that you're going to need. So let me write here that at 22 degrees, the vapor pressure of H2O is 19.8 millimeters mercury. All right, so that's a very important piece of information that you're going to need in order to answer this question. Okay, so you have the equation, and the question says, what volume of the wet gas will be collected in the reaction of 1.5 grams of aluminum with excess hydrochloric acid? So what I'm going to do is start off with the 1.50 grams of aluminum. And what I'm going to try to do is find a number of moles of hydrogen. So first we have to find a number of moles of aluminum, right? So aluminum has a molar mass of 26.96? 26.96?
98.
98. So 26.98 grams of aluminum will go down here, and here I'm going to put 1 mole of aluminum. So this will cancel out with that, and then the mole ratio between the hydrogen and aluminum, based on the equation here, is a 3:2 mole ratio. So you're going to have 3 moles of hydrogen above, 2 moles of aluminum below. And then we calculate that. (1.5) divided by 26.98 times 3 divided by 2. So according to my calculations, this works out to be equal to 0.363. So 0.0834 moles. All right? Now, the next thing we need to find, now this would be the moles of hydrogen, of course. So the next thing we need to find is the volume of hydrogen, because basically what you're gonna need is this equation. Volume is equal to nRT over P, right? So these are all values. The number of moles and the pressure here would be for hydrogen. So what we need to find is the pressure of the hydrogen. So let me put H2 here. So the pressure of the hydrogen would be equal to the barometric pressure minus the vapor pressure of water at that temperature, right? So the barometric pressure, they said, is 742 torr. I'm sorry, yeah, that's the barometric pressure. And then the vapor pressure of water, we looked it up, it's 19.8 millimeter mercury, which is the same thing as torr, right? So let's see what that gives. 742 minus 19.8, 9.8. So according to my calculations, this works out to be equal to 722 torr. 22 torr. All right. So that would be the pressure of the water. So now we put all those numbers into this equation. The number of moles that we calculated here, which is 0.0834 moles times R, which is always 0.0821 liters atmospheres over mole Kelvin, multiplied by the temperature, which is 22 degrees, which you have to convert to Kelvin. So that's 293 plus 22 gives you 315 kelvins. So that goes here. And then we divide all of that by the pressure, which we calculated here, which is 722 torr, which we have to convert to atmosphere. So we're going to multiply that by 1 atmosphere over 760 torr. All right, and that's basically the setup. So let's see what this gives. 0.0834 times 0.0821 times 315 divided by 722 divided by 760. Okay, so the answer I got, and please correct me if I'm wrong, but the answer I got is 2.27. And the units here would be liters. All right. So that's what I got. All right. Okay, any questions? Oh, a few of you came in. That took wrong. Good to see who came in late. Okay, Betsy is here. Let me see here. Bragg? Yes. Okay. Cordell? Here. Chestnut? Colwood? Here. Erlandson? Here. Green? Kennedy? Leonard? Small? Swistak? All right. Okay. Any question about this exam? Any questions? Any questions? No questions? Okay, so moving along. So what we're going to talk about next is something that we mentioned before, but we're going to look at it in more detail. We're going to look at some quantitative aspects of the kinetic molecular theory. So remember, the kinetic molecular theory is the model that we use to explain all the gas laws that we discussed. Boyle's law, Charles' law, you know, all those gas laws that we have covered before. We made one major assumption that the gas would be an ideal gas. And we're going to talk about what we mean by that term, ideal gas, as opposed to real gases. So basically, these are the principal assumptions of the kinetic molecular theory, right? Again, these are all assuming that we're dealing with an ideal gas, right? The first one is that a gas is made up of random molecules that are moving in a random fashion. Pretty much straight line motion is associated with the movement of these particles unless they collide with each other or they run into the walls of the container. But otherwise, they'll be traveling in straight lines. On average, the second point here is that the molecules are so small that basically they are far from each other. And therefore, if you have a gas in a container, that is mostly empty space. You do have the particles there, but the particles are very small, and the distance between them on average are very far from each other. The third point here, which is very important as it relates to ideal gases, is that there are no type of intermolecular forces that exist between the particles, right? So basically, the particles are moving around pretty much randomly, independent of each other. And then it says here, in the fourth assumption, the molecules may gain or lose energy as a result of collisions. However, the total amount of energy is constant. And I think a term that is used in physics when it relates to this type of collision where you have molecules colliding and you have energy being transferred from one to the other, but the total net change of energy is zero, basically. I think the term in physics they use is that they say that the collisions are elastic. In other words, you have the direct transfer of energy from one particle to another upon collision, all right? Okay, so those are basically the principal assumptions of the kinetic molecular theory. Based on those assumptions, this equation has been derived. You don't need to memorize or even know this equation, right? But the reason why I'm pointing out this equation here is that it shows you the relationship between different properties displayed by gases. So just to briefly describe what this equation is saying, P is the pressure of the gas, is equal to 1/3 times N, which is the number of molecules, divided by V, which is the volume of the gas, times M, which is the mass of the gas molecule, times this term. Now, this term here is called the average of the squares of the speeds of molecules. In other words, if you have, of course, there are billions of molecules present in any sample of gas that you might have. So what this particular term is saying is that if you take the speed of gas molecule 1, square it, add that to the speed of gas molecule 2, square it, add it to the speed of gas molecule 3, square it, and so on until you get to the billionth molecule, N, and you square that, and then you divide all of that by the total number of molecules, billions, right? Then that would be equal to the mean of the square, which is represented by this right here. The average of the squares of the speeds of the molecule, right? So that's what that term means, right? So basically, this equation is telling you, for example, that, and this is based, as I said before, the equation is based on the kinetic molecular theory. So for example, if you look at the relationship between the number of molecules and the pressure, you see that as the number of molecules increases, the pressure will increase, which makes sense, right? More molecules they have, greater the collisions that the molecules will have with the walls of the container, and therefore the pressure will increase correspondingly. Another thing that you notice is that there's an inverse relationship between pressure and volume, which we already know from Boyle's law, right? As the volume decreases, the frequency of collision between the molecules and the walls of the container will increase, and that would correspond to an increase in pressure. Now, this one, I don't think we have actually met this incidentally, but basically what this is telling us is that the heavier the molecule, the greater the pressure, right? So basically, if you compare two molecules, let's say you compare hydrogen, which has a molar mass of about 2, to oxygen, which has a molar mass of about 32, everything else being the same, oxygen will exert a greater pressure compared to hydrogen because of the greater mass. And of course, we have this term here, which relates to the speed of the molecules, which again makes sense. The greater the speed of the molecule, the harder they will hit the walls of the container that they're in, and therefore the greater the pressure that will be exerted on the walls of the container, all right? So that's basically what that equation is saying. As I said before, you don't need to memorize this equation. I'm just showing you this so that you see the relationship between, the different properties like pressure, volume, and so on. Okay, based on that equation, another equation can be derived. And that is this equation right here. Again, this equation you don't need to know or memorize. This equation relates the kinetic energy on average of the gas molecules to the temperature, because 3/2 is a constant, R is the molar gas constant, which you already know, and Na is Avogadro's number, which is also a constant. So basically, we can simplify this equation this way. The total kinetic, or I should say the average kinetic energy displayed by the molecules is equal to a constant multiplied by the temperature, all right? And again, the temperature must be in Kelvin. And again, this is something that I think we already touched upon. Basically, the greater the temperature, if you impart more energy to the gas, the greater the temperature, the faster they will move within the container, and therefore the greater kinetic energy will be displayed by the gas particles. All right. Okay. So let's talk about molecular speeds. All right. Of course, as we all can imagine, that if you have a sample of gas trapped in a container, they will not all travel at the same speed, right? Some will be slower, some will be faster, but most of them will have a value somewhere in between. All right. So this leads us to one way of basically having a representative number for the speeds of molecules, and we call that the root mean square speed, which is the square root of the average of the squares of the molecular speeds. All right. So if you remember, I said that this is equal to this. All the way up to the nth molecule, right? The squares of the speeds of the molecule will be equal to, I'm sorry, one more thing, divide by n, very important. So this here, which is the speeds, the square of the speeds of the molecule will be equal to, and that's the average, will be equal to the sum of all of these here squared, each of them squared divided by the total number of molecules, right? So when we're talking about the root mean square speed, we're talking about the square root of this, which is the square root of all of this right here, all right? So we use this as a proxy for the speeds of a molecule, basically. And we look at that in terms of relating to other properties, which we're going to discuss shortly, right? So this is what we're looking at, the root mean square speeds, right? Now, it turns out, I won't show you, of course, how this is derived, but it turns out that the root mean square speed can be calculated based on this equation right here. The square root of 3RT over the molar mass. However, you have to be careful when you're using this equation here, right? Because I'm quite sure you're familiar with R being equal to 0.0821 liters atmospheres over mole Kelvin, right? We're all familiar with that, right? Well, in this case here, we're using a different value of R with different units. And the value of R we'll be using here is 8.31 joules per mole Kelvin. All right, so please make a note of that. In this equation, right, if you're going to use this equation to calculate the root mean square speed, then this is the value of R along with the units that you need to use, right? Another thing too you need to keep in mind is that as far as the molar mass is concerned, I'm quite sure you guys are familiar with the fact that the molar mass units would be moles per gram, right? Well, in this particular equation, you're going to use instead moles per kilogram, right? So whatever the molar mass of the substance you're going to use, you're going to convert it from, I'm sorry, not moles per kilograms, I'm sorry. I made a mistake here. This should be, what I should have said is that we're familiar with the units being expressed in grams per mole. Right? But in this case, you're going to use kilograms per mole, all right? So kilograms per mole must be the units of the molar mass that you're going to use if you're going to use this equation to calculate the root mean square speed, all right? Now, let me briefly explain why those two changes are necessary. What I'm going to do is, instead of using the actual values of R, T, and M, I'm going to plug the units in here, right? So the units of root mean square speed will be equal to the square root of R. Now, the units of R is 8.31 joules per mole Kelvin times T, which is in Kelvin, divided by M, which would be kilograms per mole. All right. Now, in this particular case, the mole units will cancel out, the Kelvin units will cancel out, and you're going to end up with square root here, square root of joules over kilograms. Now, the thing about the joule unit, and you're going to learn this in the next chapter, the joule unit is the same thing as kilograms meter squared over second squared, right? So joule is the same thing as this collection of units right here. So if you put that into this, where joules is here, you're gonna get square root of kilograms meter squared over second squared divided by kilograms. The kilograms will cancel out, so you're gonna end up with square root of meter squared over second squared, which is the same thing as meters per second. All right? So basically, the units of the root mean squared speed would be meters per second based on those units that you see here, right? So that's why it's very important when you're using this equation, make sure that you're using R being equal to 8.31 joules per mole Kelvin, and whatever the molar mass is, you must convert it to kilograms per mole. So typically we would use grams per mole, but in this particular case, you have to divide that value by 1,000 to get the equivalent value in kilograms per mole, and then you plug those numbers into that equation, and you're going to end up with your root mean squared speed value. Yes, sir.
How does meters squared and kilograms squared meter?
You're going to see that in the next chapter. You're talking about this right here? Here?
The answer, yeah.
No, this is second, sorry.
Oh, that's second.
Yeah, I'm sorry, that's my poor handwriting. This here should be second squared. It should be second squared. Sorry. Okay, so it's very important that you keep that in mind. Again, this is one of those things where students commonly make mistakes, especially when it comes to the R value. They put the wrong R value, which results in the final answer being incorrect. All right. Okay, so that's basically how we calculate what is called the root mean squared speed, right? And there are a couple of things. Is it okay for me to clear this up? Erase all this. All right, let me do that. Okay, now there are a couple of things I want to say based on this equation right here. Typically what you'll find is that the speeds are very high for the molecules, about, 1,000 meters per second, give or take. But also I want to point out the relationship between the root mean squared speeds and the molar mass, right? If the temperature is constant, then basically there's an inverse square root relationship between the molar mass and the root mean squared speed. So what does that mean? That means that the heavier the molecule, the slower would be in speed at the same temperature. So if you compare two gases, let's say again, hydrogen and oxygen, and you could be asked a question, which one travels faster? Well, the answer would be hydrogen, because hydrogen has a molar mass of 2, oxygen has a molar mass of 32. So oxygen, being the heavier molecule, will travel more slowly. All right. Okay, now, let's look at what we have here on the next slide, which are two graphs. We're going to focus on the first one here, the one on the left. And this shows you graphically the relationship between what I just mentioned, the speeds of the molecules and the molar mass. So let me explain what we have here. Plotted on the y-axis, we have the relative number of molecules. Plotted on the x-axis, we have the speeds. And then we have three curves, which shows you the distribution of speeds for three different gases. Oxygen, which is the pink line, I think it is. Methane, which is the green line, and hydrogen, I think that looks purple, which is down here, all right? So these are the distributions of speeds for the different gases. Now, to get the root mean squared speeds directly from the graph, what you'd have to do is identify the peak of each curve and then drop a vertical line down until it cuts the x-axis. So I'm going to do my best to see if I can achieve that. So if I drop this vertical line down to cut the x-axis, it gets to about here. So what do you think this is? I know this is 500, right? So this looks like what? Okay, let's say 400 meters per second, all right? And then we do the same thing for the methane. So if I drop a vertical line down. Okay, so that's definitely between 500 and 1,000. What say you?
700.
Okay, let's go with that. And then for the hydrogen, this is kind of easy because this is 1500 here, so for hydrogen, that's 1500, right? So what we see here is that as you go from oxygen to methane to hydrogen, you see that the root mean squared speed of the gas increases, all right? And that's because oxygen has a molar mass of about 32, methane has a molar mass of about 16, and hydrogen has a molar mass of about 2, right? So basically, as I said before, the lighter the gas, the faster it travels at the same temperature, right? So that's what is being shown here for the graph on the left. For the graph on the right, same plot, but for one gas at different temperatures. 273, 1000, and 2000 Kelvin, right? So for 273, it is the same as here. The speed, root mean squared speed will be 400. In the case of at 1000, I drop this vertical line down here. What do you think this is? This looks like 600?
Yeah.
And then for this one here, this is almost 1500. I'd say 1400, right? So what you find in this case, as the temperature increases, the root mean squared speed of the gas increases. Again, we already know that, but this is just a graphical demonstration of that, all right? Okay, any questions about these graphs? Any questions? Okay, so let's talk about two terms, diffusion and effusion. We won't spend much time on diffusion, but let me define it first and then we'll talk about it briefly. Diffusion is a process by which one substance mixes and spreads through another substance as a result of the translational motion of the molecules, all right? And the thing about diffusion is that we cannot use it as a proxy for measuring the speeds of gas particles, all right? Because what happens is that as one gas spreads into another, they will collide with each other. And basically, you won't be able to get much information in terms of the relative speeds of a gas, all right? So as stated here, the diffusion of gases is much slower than would be predicted by the molecular speed equation that we talked about, and that is due to the frequent collision of molecules. In order for us to make any meaningful measurements of speeds of molecules, you have to have a process where you don't have collisions between particles, or you limit that, all right? And the last line here is just saying that the average distance a molecule travels between collisions is called the mean free path, right? So as long as there's a mean free path, we cannot use the equation that we saw earlier to make any calculations about the gas particles, all right? So that's diffusion. Now, here's a very interesting situation here. And I want you to think about this and see if you can come up with an explanation why we observe what we observe. So what we have here are two bottles, one containing concentrated hydrochloric acid, the other one containing concentrated ammonium hydroxide, all right? Now, what happens is that there's going to be a reaction between the ammonia from the ammonium hydroxide plus the hydrogen chloride from the hydrochloric acid. Because these are concentrated, if you open up the bottles, you're going to see fumes coming from each of them. In the case of hydrochloric acid, that would be hydrogen chloride. In the case of ammonium hydroxide, that would be ammonia, right? So when these two gases come into contact with each other, they will form a salt, a solid, ammonium chloride. All right? Now, if you put these bottles in close proximity to each other and you wait a while, eventually what will happen is that the fumes will come into contact with each other. However, the fumes will come into contact closer to the opening, the mouth of the bottle of the concentrated hydrochloric acid and not near the mouth of the bottle of ammonium hydroxide. So my question to you is, based on what we have just learned about molecular speeds, why is it that the ammonia and the hydrogen chloride will react with each other closer to the source of the hydrogen chloride and not at the source of the ammonium hydroxide?
The heavier gas.
Which one is heavier? What's the molar mass of hydrogen chloride? Hydrogen is about 1, chlorine is about 35.5. So hydrogen chloride will be 36.5 approximate, right? And what's the molar mass of ammonia? Ammonia is about 17 because nitrogen is about 14 and then plus 3 hydrogens. So that's 14. So that's 17. So which one is heavier? The hydrogen chloride, right? So therefore it will move more slowly, as you just suggested, right? And therefore the point of contact will be closer to the source of the hydrogen chloride compared to the ammonia. I remember when I was in high school, my teacher at the time, he did a little simple experiment where he had a tube and plugged at each end of the tube are 2 pieces of cotton. This one is soaked with ammonia, aqueous ammonia, and this will be soaked with aqueous HCl. And then you sit and wait a while, and what happens is that you're going to have a ring, a white ring of ammonium chloride, which is formed closer to the cotton, which is soaked with the hydrogen chloride, right? Again, that is due to the faster speed of the ammonia compared to the hydrogen chloride. Okay, so that's what happens in this case, all right? Okay, so let me, so I stated down here in the green box below to the right, the ammonia molecules move faster than the heavier HCl molecules. Okay, so that's diffusion, and that's all we're going to say about diffusion. What we're going to talk about here is another phenomenon displayed by gases, and that is effusion. And let me just say that in some chemical literature, textbooks and so on, there's sometimes confusion between those 2 terms. In some textbooks, I've seen them talking about diffusion as if they mean effusion, right? But they're 2 different things. Diffusion is where you have one gas being spread into another gas. In effusion, what is happening here is that you have the gas particles escaping through a tiny hole from its container into a vacuum. All right, so that's the difference between effusion and diffusion. And the thing about diffusion is that we can use this as a way of applying the equation that we met before, which deals with the root mean squared speed. In fact, based on that equation, we have what is known as Graham's law of diffusion, of effusion. See, I'm even confusing. And basically what this law says is that at a fixed temperature, the rate of effusion of gas molecules are inversely proportional to the square root of their molar masses, right? And that is based on the equation that we met earlier. So if we have 2 gases, gas 1 and gas 2, the rate of effusion of gas 1 divided by the rate of effusion of gas 2 can be basically calculated based on their root mean squared speeds. And that's what each of these terms represent. This represents the root mean squared speed of gas 1. This represents the root mean squared speed of gas 2. So if you divide this by this, the 3 RTs will cancel out, and you're going to end up with the square root of M2 over the square root of M1 being equal to the rate of effusion of gas 1 divided by the rate of effusion of gas 2. So there's an inverse square root relationship between the rates of effusion of gases and their molar masses, all right? And that is demonstrated in this diagram right here. The heavier molecules will move more slowly, so they fuse more slowly. And then what you'll find remaining here is that you're going to have more heavier molecules remaining inside the container here, all right? So that's Graham's law of effusion. So let's utilize this law to solve this problem. So just to remind you, the law says that the rate of effusion is directly proportional to 1 over the square root of the molar mass. All right, that's basically what this law says if the temperature is constant. Okay, so this question says, if compared under the same conditions, how much faster than helium does hydrogen effuse through a tiny hole? So basically what this question is saying is comparing the rate of effusion of hydrogen to that of helium. All right, so based on Graham's law of effusion, that would be equal to the square root of the molar mass of hydrogen divided by the molar mass of helium. Or actually the other way around, because it's inverse square root. So let me correct that. So it's the square root of the molar mass of helium divided by the molar mass of H2, all right? So all we have to do is go to the periodic table and we look at the molar mass of helium, which is 4.00, where is it? 4.002 grams per mole divided by the molar mass of hydrogen, which is 1.008 grams per mole. And let's see what that gives. 4.002 divided by 1.008. And according to my calculation, we find the square root of that. So this is, oh, I made another mistake. Can somebody tell me what the other mistake I made is? Exactly, the molar mass of hydrogen would be 2 times 1.008. So that would be, oops. So that would be 2.016 grams per mole. All right. Okay, so let's see what that gets. 4.002 divided by 2.016, and then I find the square root of that. Okay, so according to my calculations, this would equal to 1.41. So therefore, the rate of diffusion of hydrogen would be equal to 1.41 times the rate of diffusion of helium. So what this is telling us is that the rate of diffusion of hydrogen is 1.41 times faster than that of helium. So let me just say that here. Rate of diffusion of hydrogen is 1.41 times faster than that of helium. Right, so that's how you do that. All right. Any question about this? Any questions? Any questions? Okay, may I move on? All right. So here's another question. Now, this one you have to be careful about, right? Because, well, let me read the question. It says 1% of a measured amount of argon escapes through a tiny hole in 77.3 seconds. 1% of the same amount of an unknown gas escapes under the same conditions in 97.6 seconds. Calculate the molar mass of the unknown gas, right? Now, in this case, they did not give you the rates of diffusion. They gave you the time of diffusion, right? And if you understand the relationship between rate and time, you know that that's an inverse relationship, right? The faster the rate is, basically the shorter the time and vice versa, right? So what I can do is I can write down a relationship between the rate of diffusion of argon divided by the rate of diffusion of the unknown gas. I'm just going to use G for that. That will be equal to the square root of the molar mass of the gas divided by the molar mass of argon. And that would also be equal to the time of diffusion of the gas divided by the time of diffusion of argon. So in actual fact, this is the part that we're going to use here in order to solve this problem, because the question gave us the time of diffusion for argon, it gave us the time of diffusion of the gas, and we know the molar mass of argon. So all we have to do is rearrange the equation to solve for the molar mass of the gas. And as we all know from your algebra classes, if you want to get rid of the square root sign, what do? You square both sides, right? So when you do that, you're going to end up with mg over MAR, and that's equal to TG over TAR squared, right? And then to find mg, that will be equal to MAR, molar mass of argon, multiplied by the time of diffusion of the gas divided by the time of diffusion of argon, all of that squared. So all we have to do now is put the numbers in. So mg is equal to, the molar mass of argon is 39.95?
Yeah.
All right, 39.95 grams per mole, multiplied by the time of diffusion of the unknown gas, which is 97.6 seconds, divided by the time of diffusion of argon, which is 77.3 seconds. And then we do the calculation. Oh, don't forget the square. All right, so that will be 97.6 divided by 77.3, and then I square that, and then I multiply that by 39.95, and then according to my calculation, please tell me if I'm wrong, but according to my calculation, I got 63, okay, so 63.7 grams per mole. And that's how you do that. All right, so very important that you read the question carefully, right? Make sure that you interpret the question such that you understand whether or not the question is referring to either rates of effusion or time of effusion, and that's important. Okay, any questions about this? Any questions? Any questions? Any questions out there in Zoom? Okay, I'll take that to mean that you're okay with what we have done so far. All right, so we're going to finish up this chapter by talking about the difference between real gases and ideal gases. So far, in all the calculations and all that we have looked at in this chapter, we were assuming that the gases were behaving ideally. Now, what does that mean? Basically, there are two main things that makes a gas an ideal gas. And I'm going to see if I can make a note up here. One is that the volumes of the gas particles are effectively zero. Right? In other words, basically we're assuming that the particles does not take up any space at all, right? The second assumption we're making for an ideal gas is that there are no intermolecular forces between them. No intermolecular forces between the gas particles, right? These are the two basic assumptions that we're making when it comes to ideal gases, all right? However, it turns out that in real gases, those two things are not absolutely true. For one, you do have intermolecular forces that exist between gas particles. They might be weak, but they exist. And then the second thing is that, of course, gas particles have a non-zero volume, all right? So, because we have those two facts, which makes real gases not ideal, we can, however, alter conditions such that real gases behave more like ideal gases, right? So as stated here, the question is being asked, under what conditions of temperature and pressure will number one and number two be important? All right, and the answer is under, excuse me, under the conditions of low temperature and high pressure. So if the temperature is low and if the pressure is high, then the behavior of gases will become less ideal or more real, if you want to look at it that way. So if you want the gas that is real to behave more like an ideal gas, then basically you either, or you can do both, meaning you either, or you will increase the temperature or decrease the pressure. So under conditions of high temperature and low pressure, then real gases will behave more like ideal gases, all right? Now, this is explaining here the difference between real gases and ideal gases in terms of the intermolecular forces. The diagram on the left basically shows you what happens when this gas particle is hitting the wall of the container. Remember, the pressure exerted by the gas is a manifestation of the continuous bombardment of gas particles against the walls of the container, right? So in the case of an ideal gas, because this particle is not influenced in any way by these particles surrounding it, it is free to hit the wall of the container as hard as possible, right? However, in the case of an ideal gas where you have forces of attraction between this gas particle and the surrounding gas particles, then there's a drag that this will experience, and therefore this will not be allowed to hit the wall as hard as in this case. So therefore what you'll find is that if you compare real gases versus ideal gases, the pressure exerted by real gases will be low at the same temperature, same conditions and everything, all right? So that's demonstrating one important difference between a real gas and an ideal gas, all right? So remember we talked about earlier the ideal gas equation. So this begs the question, how does that equation change when we take into consider real gases? Because the ideal gas equation is for ideal gases. So a guy by the name of Van der Waal, he did some work, some theoretical work, and he came up with an equation which is basically a modification of the ideal gas equation, right? So this is the original ideal gas equation, PV is equal to nRT, right? So basically Van der Waals, based on this work, came up with some additional terms. So in addition to the pressure, he added this term right here, and in addition to the volume here, he added this term right here. And you'll notice that there are two constants that are present in each of these parts here. You have the A and the B. The A is a term related to the intermolecular force strength, and the B is related to the volume of the gas molecule in liters per mole, right? So once you take those two terms into account, then basically this works as far as the Van der Waals equation is concerned. And please note, the A and B terms are basically unique to the gas itself, right? So each gas would have their own values of A and B, right? And as stated here, those values can only be determined by experiment. So you cannot just look at the molecule and determine what A and B would be. And I think the next slide has some gases and their A and B values. So this is a combination of A and B for helium, argon, and all those other gases, all right? Now, there's one graph which I thought I had here. Let me see if I can find it online, which shows you the difference graphically between ideal gases. I thought I had saved it on this, but maybe, you know what? Let me see if I have it on my phone right here. Not, you're not at the search. I'll search for it, but I think it's important that I show you this because it shows basically in a graphical sense, here it is. It's paraphrasing. No, that's not it. Okay. Okay, this is it. Okay, so this is a plot. Let me explain what's happening here. Of PV over RT, which will be plotted on the y-axis here, right? And versus pressure here, all right? And based on what we know about the ideal gas equation, now in this case here, PV over RT, well, we know that PV is equal to nRT, right? So N would be equal to PV over RT. No, this is not exactly the graph I was looking for. But let me use this one to illustrate anyway. There's a different graph which I'm going to look for. So this is the equation right here. All right. In this case here, N is equal to 1. So basically this is set to be equal to 1. And what they have done here is that they did plots of PV over RT versus P at different temperatures. So the red line here is 200 Kelvin, The blue line is the data gotten from at 500 Kelvin, and the yellow line 1000 Kelvin, right? And what you notice here, and this is basically, this dotted line here would represent the plot if the gas were ideal, all right? So PV over RT is going to be equal to 1, regardless of what the pressure is, if the gas was ideal. But the gas is not ideal, right? At 200 degrees, 200 Kelvin, this is a plot. And then you notice that at 500 Kelvin, the line becomes more flatter, right? Or the curve becomes more flat, right? And then at 1000 Kelvin, it becomes even more flat. So in other words, basically, as the temperature increases, it's approaching the plot for the ideal gas, all right? So if you continue to increase the temperature, eventually you're going to get to a straight line like this, which would basically suggest that the gas is behaving ideally. This is not exactly the graph I was looking for, but this illustrates the difference between the ideal and real gases, graphically speaking, all right? Okay, now with that said, let me go back to the assignments. Where did we stop the last time? Okay, so I remember. Did we do number 10?
I don't think we did it together. I think last class, we just finished learning it. Dean's supposed to do it on our own.
Oh, okay. Well, did anybody try? No? Okay, let's do this together. So this question says a mixture of gases is made by connecting a 7.50 liter flask containing nitrogen at 2 atmospheres to a 13.0 liter flask containing hydrogen at 1.0 atmospheres. So the first question is, what is the volume? What is the final volume of each gas? Well, when it comes to questions like these, I like to draw diagrams. It gives me a visual of what we're dealing with so that I can tackle it more successfully. So let's say this is one flask connected to another flask. Okay, and let's say we have the means by which we can separate the two flasks. Okay, so this is nitrogen, right? And according to the question, the volume here is 7.50 liters. And the pressure is 2.00 atmospheres. And then for hydrogen, the next flask, the volume is 13.0 liters. And the pressure of the hydrogen is 1.00 atmospheres, all right? Okay, so let's say we open this up. Right? Okay, so what's the final volume of each gas? I'm sorry. What's the final volume of each gas when they mix together? Exactly. 7.50 liters plus 13.50 liters, which will give 20.50 liters, right? So that answers that question. Now the next question is asking, what is the partial pressure of each gas? So basically after mixing, right? After mixing, how do we get a partial pressure of each gas? Say what?
5 nines.
Well, you have to do something first. You do have to divide by, well,
Boyle's law.
there you go. Say the magic words. Boyle's law. Let me clear this first.
In your addition.
It should be 13. One on.
Oh, 13.0. Sorry, okay, thank you. So this should be 13.0. If that's the case, then this would be 20.5. So one decimal place. So this would be 20.5 meters. Thank you. Okay, so. What am I doing? Scrolling down. Okay, so the question is asking, what is the partial pressure of each gas? Let me erase this here. Okay, so somebody said Boyle's law. So how would Boyle's law apply in solving this problem? Let's deal with each gas in turn. Let's deal with for nitrogen. Right? How would you calculate the partial pressure for nitrogen based on Boyle's law? Let me remind you what Boyle's law says. P1 V1 is equal to P2 V2. Excuse me. What is P1 for nitrogen? What's the initial pressure for nitrogen?
2 atmosphere.
Hmm?
2 atmosphere.
2.00 atmospheres, okay? And what would be the initial volume of nitrogen?
7.8.
7.50 liters, right? What would be the final volume of nitrogen? Hmm?
20.5.
20.5 liters, all right? So therefore, P2 would be equal to P1 V1 over V2. So that would be 2.00 atmospheres times 7.50 liters, all divided by 20.5 liters. So let's see what that means. 2 times 7.5 divided by 20.5. So according to my calculations, this works out to equal to 0.731. And the answer would be an atmosphere, all right? So that's the calculation for nitrogen. What's the calculation for hydrogen? What's P1 for hydrogen? 1.00 atmospheres. What's V1?
13.
13.0 liters. And V2 would be 20.5 liters, right? Just like before, right? So P2 in this case would be 1.00 atmospheres multiplied by 13.0 liters, all divided by 20.5 liters. And then we do the calculation. Let's see what we get here. So that's 13 divided by 20.5. So according to my calculations, this works out to be equal to 0.634, 0.634 atmospheres. So these are the two answers to that question, the partial pressure of each gas. All right? Any question about it? Any questions? Any questions? Okay, the C part says, what's the total pressure of the mixture? That's easy, right? What's the total pressure? PT would be what? Hmm?
3 atmospheres.
I don't know. No, that's not it. How do you get a total pressure? Remember Dalton's law?
Add the 2.
Exactly. You add the 0.731 atmospheres that we got before, plus the 0.634 atmospheres. And let's see what I get. 0.731 plus 0.634. So according to my calculation, this works out to be 1.365 atmospheres. That's it. That's where you get the C bar. All right. Any questions? Any questions? Okay. Is it okay for me to clear this? All right. Okay, this one says, number 11, 193 mils of oxygen was collected over water on a day when the atmospheric pressure is 762 millimeters mercury. The temperature of the water was 22 degrees. How many grams of oxygen were calculated? So this is one of those situations where you're collecting gas over water. And remember, we said in this situation here, the gas that is collected over water will contain water vapor. So therefore, we can say that the pressure of the gas, in this case oxygen, that would be equal to the barometric pressure minus the vapor pressure of water, right? Now, the barometric pressure is this, 762. I don't know if I told you this, but the barometric pressure is the same thing as the atmospheric pressure, right? So whenever you see those two terms, they mean the same thing, right? So the barometric pressure is 762 millimeters mercury minus the vapor pressure of water, which is 19.8 millimeters mercury. We see what that gives. 762 minus 19.8. So according to my calculation, this works out to be 742 millimeters mercury, all right? And then, okay, so we have the pressure of the oxygen, we have the volume of oxygen. What else we have? We have the temperature, and the question is asking for the grams, right? Now, there's one equation that we met before, which is M, the molar mass of the gas, is equal to lowercase m, which is the mass in grams, divided by RT over PV. Remember that equation, right? We can rearrange this to solve for lowercase m, which is what the question is asking for. So lowercase m would be equal to molar mass times pressure times volume over RT. And then all we have to do is put the numbers in. Now for oxygen, the molar mass is 32.00 grams per mole, multiplied by the pressure. What's the pressure? 742 millimeters mercury, which we have to convert to atmospheres. So 1 atmosphere over 760 millimeters mercury, and then multiply by the volume. What's the volume? 193 milliliters, which we have to convert to liters. So 1 liter over 1,000 mils. And then we divide all of that by R, which is 0.0821 liters atmospheres over mole Kelvin, multiplied by the temperature, which is 22 plus 293, 315 Kelvin. And that's the setup. And in terms of units canceling out, this mole will cancel out with this mole, this Kelvin will cancel with that, atmospheres will cancel out here and here, millimeters mercury cancel out there and there, milliliters will cancel out there and there, this liter will cancel out with this liter, so the only unit remaining would be the gram unit. So let's see what this gives. 32 times 742 divided by 760 times 193 divided by 1,000, and then divide that by 0.0821 times 315. So according to my calculation, how many secrets? 3 secrets, okay. So according to my calculation, this rounds off to 0.233 grams as the final answer. Yes, sir. Liters right here. Right here. Yeah. By adding 273 to 22.
That's 295.
Oh, shoot, 295, thank you. Okay. I don't know. Thank you very much. Yeah, that should be 295. That means the answer is wrong. So this should be 295. Okay, so let me do this again. V2 times 742 divided by 760 times 193 divided by 1,000 divided by 0.0821 times 295. Okay, so this time the answer is 0.249. .249 grams. All right. Okay, any questions about this? Yes, sir. Liters, right here. It is liters atmospheres over mole Kelvin. That's the units for R. Alright? Okay. Can I clear this? And scrolling down. Okay, this might be the last question. Oh, this one already? Oh, right, yes, we did do this one, yes, thank you. Okay, let's see what's further down. Oh, now we're gonna get into ground, the law of diffusion, all right? So this question says, in an experiment, it takes an unknown gas 1.5 times longer to diffuse. Now, again, let me say and stress that when you're dealing with these types of questions, you have to interpret it correctly, right? Because remember, the law talks about the rate of diffusion as it relates to the molar mass, right? Basically, the law says that the rate. I don't know what's going on here. Basically, the law says that the rate of diffusion is inversely proportional to the square root of the molar mass of the gas, right? Rate deals with how fast, right? But this question says that the gas takes 1.5 times longer, right? So what that means, it's not talking about rate, it's talking about the length of time, all right? So it says it takes 1.5 times longer to diffuse than the same amount of oxygen gas, O2. So it's asking for you to find the molar mass of the unknown gas. So the way I would set up this equation is, I would start off with the time of diffusion of the unknown gas divided by the time of diffusion of oxygen would be equal to the square root of the molar mass of that gas divided by the molar mass of oxygen, right? Now, basically, this here, the question says that this would be equal to 1.5, right? So basically, we have 1.5 on this side. We can easily get the molar mass from the periodic table, and therefore we can determine the molar mass of the gas. So what I would do is, I would square both sides to get rid of the square root sign. I would get mg over MO2. That would be equal to the square of 1.5, and then mg would be equal to 1.5 squared times the molar mass of O2. So that's 1.5 squared, and the molar mass of O2 would be 32.00 grams per mole. So let's see what that gives. 1.5 squared times 32, and according to my calculation, this works out to be equal to 72 grams per mole. And that's how you do that. All right?
You're solving
The molar mass of the unknown gas. All right? Any other questions about this? Any other question? Let's look at number 14.
1 second.
Oh, sorry. All right, so let me clear this. Now, in the case of number 14, it says, suppose a gas diffuses, and see here is where they confuse diffuse with diffuse. As I said before, in a lot of chemical literature, they use those two terms interchangeably. So this should actually be effuse, all right? It says, suppose a gas effuses 1.4 times as fast as sulfur dioxide at the same temperature and pressure. What is the molar mass of the unknown gas? So in this case, unlike the previous question, they're talking about how fast. The previous question was how long. How long has to do with time. In this case, they're asking, or they're saying that one gas diffuses or effuses 1.4 times faster. In this case, they're talking about rates, right? So the question is asking for us to determine the molar mass of the unknown gas. So the way I go about doing this is that I would say that the rate of diffusion of the unknown gas divided by the rate of diffusion of SO2, that would be equal to 1.4, and that would be equal to the square root of the molar mass of SO2 divided by the molar mass of the unknown gas, because again, there's an inverse square root relationship between the molar masses and the rates. So again, the aim is to get the molar mass of the unknown gas. So what does that mean? That means you have to square both sides. 1.4 squared will be equal to the molar mass of SO2 divided by the molar mass of the unknown gas, which means that the molar mass of the unknown gas would be equal to MSO2 divided by 1.4 squared. The molar mass of the SO2. So now we have to add this up. Sulfur is 32.07 plus 2 oxygens, so that's 32. So this gives you 64.07 grams per mole divided by 1.4 squared. So divided by 1.4 squared. So according to my calculations, this would be equal to 33 grams per mole. And that's it. So again, you need to interpret the question carefully to see if the question is referring to either rates of diffusion or time of diffusion, right? So, you have to, make sure that you interpret the grammar of the question correctly so that you use the right explanation. Okay, any question about this? Oh, 2 minutes left. All right, so we would have time to do that. I would suggest that we try to do the others. Let me see how many questions are there. 15, 16, 17, 18. Okay, so you have 4 more questions. All of them have to do with the Graham's law of diffusion. So try them. If you have any problems, feel free to contact me. Let me remind you also of your test next week, this time, and that test will cover chapters 3, 4, and 5. So that's today.
That can be Thursday.
Next week, Thursday. Okay, so this is what I want you to do. I'm going to set up a job box for this assignment here, because I need to grade it and get it back to you so you can have it to review for your test. Let me see. Okay, so let me do this. Let me go to assignments. Okay, so assignment number 5. Okay, so that's today. I'm going to let it be due by Saturday. All right. Now I'll make myself available online if you have any questions. So let me do that now, because I want to grade it and get it back to you so that you will have it to review. So let me see here, available from today. Saturday. And in fact, what I'm going to do, because of the closeness to the test, I'm going to publish the answer key on Sunday, so that you have the answer key to look at. But I do expect the assignments to be in by Saturday midnight. All right. All right. So that's it.
Our next slide.
Is that the sequence of chemical reaction?
Yes.
Yeah, I think so. Yes. Yes, ma'am. Let me see. It's this one is basically that's 1 through 3. Let's check it to see. Okay, so this one seems to have. Okay, so I'm going to publish this here. This is basically test 1 through 3. So you can look at it and identify those topics that the next steps will go. And let me make sure I publish that, because sometimes I forget to do that. So. It's okay, so it's there.
Thank you.
All right. What's that?
The doors locked.
Oh, yeah.